computer. So welcome again to everybody. We will restart this Floquet school. Now in this very last session of the day, we'll have Xavier Waintal. Xavier works at the French Atomic Energy Commission in the beautiful city of Grenoble. And he very kindly joined us today, and this will be the first of his 2 lectures. The second one will be also with Thomas Claus, who is also in the audience. So welcome, Xavier. Xavier is very well known in the field, and probably you know him as well as one of the figures behind Quant and T-Quant. And so welcome, Xavier.
Thanks a lot, Luis. Let me share my screen. Up.
Right.
Here we are. Can you see the main? I have 2 screens. Can you see the main one? Yes, perfect. Excellent. Okay. Well, so good. Yeah, as Takashi said, good evening, morning, whatever it is for you. So this is we are going to have another talk on time-dependent systems. I'm going to change 2 things with respect to the previous 2 talks. The first is that I'm not going to be interested in bulk that much, but mostly in devices, quantum and electronic devices. So I will play with different shape, with different kind of devices, interferometers, these kind of things. That's the first change that we will see. And the second is that I will be mostly interested to what happened in real time. So in that sense, I'm not sure I belong entirely to a Floquet school. Also, there will be a little bit of periodic driving, so Floquet physics. Mostly, I'm going to be interested in something in real time. So, for instance, a typical kind of things we could be interested in is we have a 2D systems where so electronic systems. We have gates here so that the electrons can only go where we say they can go. And then you send, for instance, a voltage pulse and it's going to propagate. Then maybe you can tunnel here. Then maybe you can take this path or that path. And maybe it can tunnel here. Then maybe it can interfere. And then you can detect it. And you can measure the current. So this is typically the kind of experiment I'd like to discuss. I mean, virtual experiment so far. This one has not yet been realized. That I'd like to discuss today. So here is my my outline for the two lectures. First, I'm going to introduce you a little bit to quantum nanoelectronics reserved in time. What I mean by that, I will discuss a bit the dreams of the fields, and then I will tell you where the experiments are. So this is really going to be really a seminar-like broad view. Then I will drive a little bit more into the flesh of what is interesting there. And I'm going to give you 2 examples of concepts that are there in time-dependent system, but you have no equivalent in DC. So Mark did that, and Takashi also in the previous talks is try to define things that you could get with Floquet or not in DC. For instance, you have this stabilization of topological phases due to Floquet driving. Here, I will show you two concepts. One is I call dynamical control of interference pattern, and the other one is how you can control the trajectory of the electron in real time. And I will illustrate this concept with several examples on simulations. As you will see, as I explain all these things, I will show you a lot of simulation. I'm a simulation guy, so that's what I do. What I would like to do next in the third part is to explain you really the mathematics behind what we do, how we simulate, how we do the analytical calculation. Actually, we use the same framework for both. And I'd like to slow down when I do that. So this will be more like a lecture, less like a seminar and more like a lecture. At this stage, if you have any question, then really please stop me along the way, because it's really meant for you to understand how you do the calculations. In particular, I will discuss two aspects that have not been discussed so far. One is what I call the Pauli principle problem. When you drive, you excite particular You can excite an electron to go to a null. You can, you can change energy that don't serve anymore, and you have to do that while respecting the Pauli principle. And it's not entirely trivial to do that, and I will explain how we do that in practice. I will also explain how we do the simulation directly in the thermodynamic limit. It's very important. If you are not in the thermodynamic limit, then your energy is going to increase, and you want to release your energy in your electrodes. And so I will also explain a few particle aspects. So that should take me almost all of today, and probably I will end up mid of section 3 tomorrow. And then at the end, I will actually, the final part of the lecture will not be given by me, but by Thomas, who is in the audience. And Thomas will actually show you in practice how you can actually use this formalism to make real calculation. And for that, we will make use of two packages that make your life very easy to do this kind of calculation. One is quant and one is T-quant. So really, Thomas will actually walk through the details on how you actually do your own calculation. So that's the menu. Okay, as everyone before, like, please stop me if something is unclear. Yeah, let me start. So first, let me start with the dreams of what people would like to do with this kind of systems. This is an example, for instance. You have, once again, now this is just an artistic view, but you have two rays here. Here it's very thick, here it's pretty thin. So if it is thin, then the electrons have a chance to tunnel from one side to the other. And then you're going to send a voltage pulse, so it's going to generate some sort of excitation here, like this thing propagate, and then it can actually start to tunnel and be in a coherent superposition of left and right. And if you call the left 0 on the right 1, then you could call this state a flying qubit, a flying quantum bit. So this is, for instance, something that you could try to realize. And this is a simulation here below. So you have here this two tunnel wire, and you see like an excitation propagates, and then it starts to be here, and then it's on the lower rail, and then it's again the superposition of up and down. So it oscillates between the two quantum mechanically, and eventually at the end it ends up where it started. So no big deal here. So this is one flying qubit. Then if you have one, you can try to make two. For instance, you have one flying qubit here, and then a second one with this rail here, 3 and 4. And then if you have electron-electron interaction between these two guys, then what happens on this first qubit will actually depend on what happens on the second one, and you can actually entangle the two qubits together. And this is what people are trying to would like to make, like some sort of two flying qubit gate with this. And then you can continue like that. If you believe that you made one qubit gate and two qubit gates, you can make like this kind of train circuit. So here again, you have your two rails, 0 and 1. You send your levitons, so this is the name for this excitation, so these pulses, essentially, the voltage pulses. And then they go around, and then you can actually lead them to some gates, like this, for instance, the one we had before correspond to Hadamard gate, or and then you can take two of them and make an interaction between two, and you could have a full-scale quantum computer. What is pretty nice here is that if you compare that to the kind of quantum computers that we are used to, it's actually the dual. Like here, the hardware corresponds to the gates, but you can put as many qubits as you want. Essentially, they are free. They are like photons. I mean, they are plasmons in this case. While in regular quantum computers, usually the hardware corresponds to a qubit, and then you operate just with different pulses. So the hardware footprint is very, very big. This is really like a dream, or actually not even a dream, because we are very, 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 very far from that. But I'm just showing you this so that you see that what kind of things people have in mind on why do they write all this crazy introduction to their papers. Now let's go back to what actually exists. A lot of things has been already done in DC. So this essentially in DC, it's essentially an interferometer. For instance, this is a device that has been measured in Chris Borley group. So you have 4 ohmic contact here. This is 4 forces. This is a beam splitter. So essentially here you actually use the fact that this is if you put that in if you allow tunneling through this gate, then you can get a superposition of this and that. This one you deplete entirely, so then it's going to be only the 2 paths up and down. On using this device, you can actually interference between a pass like this on the lower pass. And then depending on whether the interference is constructive or destructive, it can go up to this ohmic contact or to that ohmic contact. And as a function of magnetic field, you will see nice interference, nice oscillations, which you can also reproduce in simulations. And also you can also see oscillation as a function of this tunneling bar area and all kind of things that you can see there. So I would say in DC, this is pretty much under control. This is a zero field experiment, weak, low field experiment. You can also work in the quantum Hall regime. So there you have edge states at a large magnetic field. So for instance, you have one edge state here. Here you have a quantum point contact. So essentially it's a beam splitter. So part of the electron can go down and part of the electron can go up. And then you have a second point contact here. Then they can go up and be absorbed in the central ohmic contact, or they can actually go there from this pass or that pass. So you see you have two passes here, one upper pass and one lower pass. And that's a Mach-Zehnder interferometer, essentially the same as what you saw in electronic 101. And you can observe that the conductance actually oscillate as a function of magnetic field. And the period of this oscillation corresponds to the size of this hole here between the upper pass and the lower pass. So if you make a large system, then you see it oscillate faster than if you make a small one. This is an experiment in a group of Préven Rouleau and Patrice Roche. And you can also make nice simulation of these things. Here it's okay, not exactly the same geometry, probably you should rotate it by 90 degrees, but the physics is the same. You can see the edge state, and now you get these two passes. I'm just mentioning this, even though I will not be talking about interacting systems today, especially not about composite, about fractional quantum effects, but there are some recent experiments where this kind of interferometers also work in fractional quantum Hall regime. And then you can actually see hints of the fact that the particles here, the quasi-particles here are not electrons or bosons, but anions, something in between. And there have been this experiment here, which I find very, very nice. And so there is a lot of work in this direction going on at the moment. So we are going to talk about time-dependent things. So let me show you two experiments on time-dependent phenomena. This is an experiment in a group of Waintal in Paris. So he has two sources. I will explain in 1 second how actually make the one electron, the single electron source, but one here and one there. In the quantum Hall regime, so the electrons follow the edges. And then here you have a quantum point contact, so beam splitter. So you send two electrons, one against the other, and then they are deflected, then one can go here and one can go there, or maybe two can go there. And you look at essentially the probability to get one in one detector, depending on the as a function of the delay between the when you send the two electrons. And you see a dip here, which is so it's called anti-bunching, and it's a signature of the fact that this electron, if one is in this state, lower state, then the other one doesn't want to go to the same state because these are electrons, so there is Pauli principle. So you have more chance to find the second electron in the other output. So typically, this is the kind of experiment that people are doing at the moment in this field. You see the time delay here. We are in the picoseconds range, or tenths of picoseconds range, I would say. And just to explain a bit, there are several kind of single electron source that you can try to make here, but this particular one is using a quantum dot. So, so here you have a quantum dot with a capacitance with a gate on top. So you have an electron here, and then you raise the things, and then the electron will actually flow. And then you have to. So this is a closed system, so you can have 0 electron flowing forward in average. So then you have to go back to lower this energy, and then this guy is going to be filled again, and that means that the hole is emitted. So essentially, it's a source that emits an electron, and then a hole, and then an electron, and then a hole. But if it's slow enough, then you can actually consider that these processes are independent. So this is one experiment. On another experiment, this is also in the group of Chris Borley, where essentially he sends a voltage pulse here fast enough and this is measuring the velocity at which this propagates through the rail. And now they can do things fast enough that actually they have a chance to stops the electron with a quantum point contact here at different stage. And then depending on the time of flight, I mean, you can measure the time of flight essentially, so measure the velocity. So this is the kind of thing that is done here. I'm not going to enter into the detail. Essentially, the message here is that this field is slowly going from a zeroist field to an experimentalist one. Essentially, it's really happening now. And to conclude this introduction part, so this field is called by the players electronic quantum optics. Essentially, they need pulses a bit shorter than what they are using at the moment. So they need pulses in the 10 picoseconds range. You want your pulse to be small enough that it really propagates through the system. That if it's large pulse and you are in the DC limit, you want so you want short pulses, and they are getting there. You need detectors also. So this is something that so far everybody has been detecting things in average, so measuring current essentially. But now they are working on single electron detector, but this is coming also. And I would say that this is provides us to be a very interesting playground for us theorists when all these experiments, all these virtual experiments become reality. Essentially, this is nanoelectronics in the terahertz range, to summarize. Okay, so now we go to the theory part, and I'm going to explain you two effects, two concepts more than effect, because with at least with the first you can make many different effects, which are it's the same effect, but it takes different form in different contexts. Where you can really get some nice things going on from the fact that we are going to send pulses on the kind of things, on that I really don't know how to get something equivalent in this. Let me start with the first. This is dynamical control of interference pattern. And for that, I'm going to discuss a very simple system, just a 1D line, so 1D Schrödinger equation. I'm going to send a voltage pulse here, so some pulse that's going to propagate. And I put two barriers, one here and one there, to transform that into a Fabry-Perot cavity. So it's as simple as it gets. And so just this is a quick reminder on the Fabry-Perot cavity. One way to look at it is that you have two barriers. So if you want to calculate the total probability for something to be transmitted, so I call D the transmission, because I need the letter T for time. It's a sum of several terms. One is I am transmitted by the first barrier and then transmitted by the second one, so that's dA dB. I can be transmitted by the first, reflected by the second, reflected by the first, and transmitted by the second one. That's dB, RA, RB, dA. They correspond to the first one correspond to this trajectory, the second one to that, and so on and so forth. And if you stare at this expression for a while, you realize that it is actually a geometric series. Z is actually the phase you pick up when you make one bond trip. So it's actually a 2kFL, which you can rewrite as a time of flight times the energy of the particle. So it's a geometric series which you can rewrite like this. Okay, no big deal. And now if you plot the corresponding transmission probability now, so the square of the transmission amplitude, as a function of, let's say, some gates that I would put here that allows to change the potential in this region. So it would be a gate potential. You get these nice oscillations corresponding to Fabry-Perot oscillations. They go exactly up to 1. That's the magic of Fabry-Perot. And if the transmission barrier gets higher and higher, they slowly go to a discrete spectrum that corresponds to just particle in the box here. So essentially, as I lower the barrier, these states here get widened into this Lorentzian that correspond to the Fabry-Perot. Okay, fine. Now the stage is there. Let me send a voltage pulse on this device and see what happens. So there is one trivial limit, which is if the DC if my voltage pulse is very, very long. So if my voltage pulse is very, very long, but very small voltage, here the height is very small, I essentially am probing the transmission probability. So what I'm plotting here is the probability for the pulse to be transmitted divided by the number of electrons I sent. So the number of electrons received divided by the number of electrons sent, which essentially is the transmission probability, but generalized to time-dependent system. So if again, if the voltage is very small, I should get the same thing as a transmission probability I calculated before. Now, if I increase the voltage, then I start, you see my voltage now is not only on one resonance. Now, if I increase the voltage, it's larger than this mean level spacing delta. Then I will wash out my interferences. Essentially, I'm going to, it's not so well, my energy, the spectrum of my pulse now encompass several of these resonances, and I get something where I wash out. So this resonance is wider, it doesn't go to one anymore. This is when I open a little bit, and if I increase the bias voltage even more, then I should wash out completely the interference. So this is quite trivial. Now it's going to get very interesting when I take the same pulse, but I make it much smaller in duration. Now the duration of the pulse is going to be shorter than the time of flight between these two barriers. So the naive argument is that if the time of flight is very, very short, then h bar over this time of flight is large, which means that the energy width of this pulse is very wide. And so I should wash out totally my interference pattern. That's at least what I was expecting. You can actually reframe this argument in a different way, which I call the classical bullet limit, which means to say essentially now if this you can consider it as a bullet, it can be reflected with certain probability, or maybe it's transmitted, reflected, or transmitted. But essentially, you have no interference anymore because this thing is localized in time. So what can it have interference with? And this picture is actually partly correct. So if you do the simulation, for instance, this is position on time, and you send your voltage pulse here. You see when it reaches the first barrier, it's partly reflected, partly transmitted. And then here it's partially transmitted, partly reflected, and then you see that here again, and so on and so forth. And so the basic idea that you could have is that you can take the same law I wrote before by adding the transmission amplitude, but now we directly write it for adding the transmission probabilities, and you get the same thing here for transmission probabilities. That would be a classical Ohm law. The first one would be quantum Ohm law. That would be a classical Ohm law. Like for bullet with these two things. And this picture is not entirely correct. And if you look at the current that goes through at the end, and you plot the current as a function of time, you see that you do see these bullets here. But you also see that in between the current doesn't go to zero. And this is a bit weird. And this is actually where all the fun is, and I'm going to explain you that in a moment. So let me first give you what you should expect if you do this experiment. In principle, you should be either scared or find it like this is wrong or there's something. So I just give you the bare fact of what you find in a simulation, for instance. And just afterward, I'm going to explain you where it comes from. So don't leave me right now. It's going to be fine. So the first thing that suppose that you have this pulse here with a large voltage on long duration that gave me this blue curve. So the voltage was wide enough to wash out at least partly the interference pattern. And now the only thing I do is I make this pulse shorter and shorter in time. I don't change the amplitude, so it's still large enough to wash out the interference pattern. Oops, sorry. But I make it shorter and shorter. And what you see that when you make it very short, you recover here exactly the perfect resonance that you calculate in this. And that for me was very striking. Like because now the energy width of your pulse is very wide, the amplitude is very wide, everything is wide, so you encompass a lot of these things here. And nevertheless, everything is as if you had perfect, like a very thin window of energy. You are probing exactly one resonance. That's one weird thing. Now it gets weirder. If you plot the number of electrons that goes through as a function of the amplitude of the pulse, essentially what you send here. And you see that actually it oscillates. It oscillates, and in some cases, so here you have two cases here, left and right, it just correspond to different barrier height for the two barriers A and B. But if the barriers are pretty high, not only it oscillates, but you can even get negative current. So you are sending some pulses, and actually you're pumping electrons from the other side. And that for me made no sense at all. And so this is actually this concept of dynamical control of interference pattern. And now I'm going to give you the explanation. And it's very simple. It makes sense if you remember that we have a Fermi sea. We are not in vacuum. In vacuum, you could never observe something like that. We have a Fermi sea, and what we do is to perturb that Fermi sea by sending a voltage pulse. So if you think about it, before you send a voltage pulse, you have plane wave in your lips, in your electrons. Exponential IKX minus IET. They are there. Now, when you raise the potential by EV, you don't, in the part that fills the potential, so in the rear, you are not going as E, you are going as E plus V. So you're getting an extra phase with respect to the front part. And this extra phase is exactly the integral of the voltage that you put in unit of H bar. So the correct picture for what is going on is you have a domain, you have a plane wave, and the voltage pulse has introduced some sort of domain wall in the phase of this plane wave, right? And this domain wall is now going to propagate through my system. And so if you take, in this case, I made the drawing just with two passes. It's slightly simpler than the Fabry-Perot, but it's the same thing with Fabry-Perot. Now you really have to think that you have, when you send the pulse, it goes through the two paths, like the straight path and then the longer path. And if you look at this particular time, when it has arrived through the lower path, but not yet through the upper path, you see now I have interference here between the blue, between the front of the upper path, and the rear of the lower path. And there is this extra phase in between. And so this is what I mean by dynamical control of interference pattern. During this time, in this transient time, I have modified the interferences by this amount phi, and phi is actually just this, which is just the number of electrons that I actually sent in the system. So you see that my interference before was this, and now I pick up this extra phase, and I now can play with this extra phase to do all kinds of nice things. That might be my first concept. And I'm going to spend 10 minutes showing that you can apply it everywhere. Like you can find application to these simple things everywhere. For instance, something very simple that you can do is instead of just making a voltage pulse, so raising and lowering the voltage, you can just raise the voltage at t equals 0 and stay up. So now I still have a phase between the front and the rear, but at the rear now this phase actually just increase linearly in time. So yeah, we have three regimes. We have the initial regime where I have the regular interference pattern. The regime at the end when all so now it's not I should not write a pulse like that. It's more like I raise the voltage. It's more like a tsunami that follows things. So all the red should be up too. So at the end also you see I have the phase both on the up and lower, so it doesn't matter. But there is this intermediate regime now where I have this extra phase, but now the phase varies in time, which means that I have a current that oscillates in time at exactly the frequency EVB over H bar. And if you think about it, the mathematics are very, very close to the AC Josephson effect. So I call that the normal analog of the AC Josephson effect. It's transient. It's only during a finite duration of time, but it is there. And you can do simulation of these things. For instance, if you now I'm back to the Fabry-Perot. If you raise the potential in Fabry-Perot, you will see it's raised by plateaus here. This is correspond to the first plateau when you go directly, second plateau when you go after one trip, and third plateau and fourth and so on until you reach the stationary limit. But if you look at one of these plateaux, you find exact oscillation, I mean very nice oscillation with a frequency which is exactly EVB over H. That's my first effect. On the we apply that to a lot of things. I think I'm a bit slow. Yes, I am a bit slow. So I'm going to be very quick on the two applications. It's the same idea, but you can play with that. For instance, if you're a fan of Majorana's device, for instance, like this Majorana, one way to think about it is through Andreev reflection. So you have an electron reflected in as a hole, then it can be reflected as a hole, reflected as an electron, and so on. So it's which is also a Fabry-Perot interferometer. So you can apply that to Majorana. You can also, yeah, this is my connection to Floquet. You can also send not just one pulse, but series of pulses to stabilize these things. So for instance, in the cases of Majorana, you can actually move the Majorana around. You can start from something which is not topological and make it artificially topological. So I would say this would be some sort of Floquet topological insulator or superconductor, even though it's a bit different and it's really a 0D in this case. I'm not going to explain too much. You can play with magnetic systems. Okay, I'm just going to skip that. But essentially, if you think about, for instance, if you think about RKKY interaction in magnetic multilayers, there are also Fabry-Perot interferometers. So you can send, if you send terahertz light on them, you can actually control the magnetic exchange interaction in magnetic multilayers. Okay, that was my first effect. Now I'm going to show you a second one, actually a simpler one. Now we are going to look at the quantum Hall effect. So this is a 2D egg with 4 contacts, and I am in the quantum Hall regime, which means that I have edge state, in this case mu = 1, so I have just a single edge state on the edge. And when I start the simulation here, I have a gate here, so that actually the edge state is around the gate. It's around there. And if I send a voltage pulse here, it creates some excitation, some plasmon. And this plasmon follows the edge here, you see, follows the edge. But now I can start playing. And for instance, I can decide to put this gate to ground. I can just change this gate dynamically. And now if I do that, my new edge state is actually here on the boundary. And in the middle, well, I am in the bulk of quantum Hall system. There everything is dispersionless. So my excitation essentially gets stuck in the middle. So you can wait, and you see in simulation that nothing happens. It gets stuck. And then you can decide to put the gate again. For instance, if I put my gate here, then I have my edge state, which is back again. So now there is some dispersion states here, and this thing can start to propagate again, and is going to get absorbed by this slit. Or I can actually decide to put another gate in front. Now my edge state is here, and this is going to follow the lower edge like this, and be absorbed by this link. So I can start to play these games of changing the electron path, of playing with pulsars. I mean, you can start to see that there is a large kind of amount of games that we can play. Now let me combine the two preceding because it's fun actually. You see. Oh no! So first I need to explain you a little bit why it stops. It's not totally trivial, the fact that when you do that, when you put the gate to 0, it's going to stop the electron. And to understand it, I need this drawing here. So once again, if I put my gate on, then this is my edge state here, as you can see. And if I put the gate off, now the edge state follows the actual mesa of the system. And so I have here the two dispersion relation, energy versus K. But K is a propagation along this direction here. But in a quantum Hall system, it's also the position of the state according to the transverse direction. So you can also think of this KLB square as a position here. So with the gate on, I have this dispersion relation here, the dashed line. And with the gate off, I have this. So this is my Landau level here, flat, and then you see it rises up on the edge of the middle. Now
Can I ask a question?
Yeah, sure.
On that previous slide, Is there some like hidden time scale that determines where that pulse moves, depending on how long you wait to turn the gate back on?
Yes, but it's a very simple time scale, and it's going to be clear after I explain the next slide. The time scale, essentially, you need to switch off the gate faster than the time it takes for this pulse to go from here to there. So it's really the time of flight through along the gate that matters.
Okay, thank you.
And the reason is following. It's not entirely trivial. If you start, so this is your initial edge state. This is your Fermi level. And now when you change the gate, you see, if you think about this system, it's invariant by translation. Take a big slab of this. It's a long system. The system is invariant by translation along y. And if the system is invariant by translation along y, it means that ky is conserved, which means that even when I change the voltage, which means that when I change the voltage, k is conserved, so it can move vertically here. So I go here. So you see that I have to do that. The only thing I can do is this. And the question is whether I do this fast enough to reach this thing here before I have left the area where my lead is. Okay. And so now let me show you something fun. No, not yet. Okay, this is just the same as before, so the dynamical control of interference pattern, but for the quantumal, for Alexander made in a quantumal regime. So I send the voltage pulse. I have one trajectory that goes down here, and one trajectory that goes up here. And here you see a snapshot where the one part of the pulse is here, and the second one is about to be absorbed by a lead one or by lead two. And if you look at the current that you get in lead one, this is this plot here, as a function of time, you see there is a first bump when this lower thing arrives, a second bump when this upper thing arrives, and in the middle, well, this is where you have this modification of interference pattern. So if you plot this as a function of the amplitude of the pulse, you see this thing actually oscillate. And while the classical part is more like almost linear as a function of the number of electrons sent in the pulse. And this is actually something where you can calculate everything theoretically in this particular case. And that's now I'm going to combine this device to stop an electron with the interferometer I showed you in the previous slide. And if you do that, you get something totally crazy. So let me show you. So let's say this is the protocol. I send a voltage pulse. This voltage pulse follows the edge here. Then I stop it. So I put this gate to the ground. So this guy is stopped for a while. I wait for a time tau w. And then at tau w, I put the gate again. So I release the electron. So it continues its trajectory, and then it enters the interferometer part. So it can go there, or it can go down. And then I measure the number of electrons I get here. And you see this number of electrons. Actually, here it's number I get in one minus the number I get in two. This is where you have both signals. It doesn't really matter. When I plot this number n1 as a function of the waiting time, so the time I waited between the when I pulled off the gate and I put it back, you see oscillations. So if I wait more, I get a different number of electrons than if I wait less. And this looks very puzzling initially, but if you think about everything I said so far, it makes total sense. You see, when I put this guy to the ground, initially it was actually oscillating at an energy EF. But when it is in the ground, now it oscillates only at the energy E0, which is this Landau level. And so while this part here is still oscillating at EF on that part too. So I get a difference of phase between the inner part, which is now oscillating at E0 when it is stopped, and the outer part, which is always oscillating at EF, which means that I have extra phases acquired between this and that. And this is the same as if I had a pulse here with a number of particles NW and minus the same pulse here. So NW is Fermi energy minus the base 0 E0, the Landau level energy, times the waiting time. So what I'm really sending to this Mach Zehnder is a bunch of not one pulse, but 3 pulses. And then you can all kind of interference pattern reconstruction. I mean, you can have a one go up and you get the picture essentially. Now it's more complicated because you have 3, but it's the same picture with these 2 paths. And this is what gives you this oscillation as a function of the waiting time. Okay, so essentially that's it for the physics part. That's what I wanted to say about the physics. It's a good time for taking a few questions, and then I will go on more lecture-like. I will go slightly, I will be slower, and I will try to explain you the real mathematics. You know, before it was like the mathematics for well, explaining in conferences. Now I want to show you the actual math if you want to do the calculation yourself, on where are the difficulties and how to do that yourself. And then so we'll do that a bit today and a bit tomorrow. And then you get the final blow by Thomas, will actually show you how to do real calculation using T-quant. So if you have any questions of understanding on what I showed so far, now is a good moment, I think.
Any questions by the audience?
Right. Xavier, thank you for this good answer. Are you listening to me?
We have a Larsen.
It's book. Now it's good. Xavier, in your last slide, you showed the graph of the n-1 and n1-2. Look, could you comment again the main difference between this change in the aspect of oscillations of the yellow curve with the magenta curve, taking into account the energy levels?
No, the magenta and yellow, it's essentially the same thing here. I think I can't remember the difference. Let's consider just one. So it's same, you can consider the same thing. So once again, let me repeat the basic fact. What you do here, you send a pulse. When it is here, you stop the pulse by grounding the gate here. Put the gate ground. So now my H state is here. The pulse is stuck in the middle. You wait for a time tau W. Then you release the pulse, which means that you put this gate back. And then the pulse continues its trajectory. It's going to end up, so to take this trajectory or the lower trajectory, and you count the number of electrons that you get in N1. And you repeat this experiment to get until you have enough statistics. And what you see is that the number of electrons that you get in N1 oscillate as a function of tau W at this waiting time. And the reason, I mean, if you really want to understand the details, probably you need to, take a big deep breath, read the paper on the. but at the end of the day, it boils down to the fact that this voltage pulse, it really modifies the plane waves. That it only modifies the full Fermi sea, if you want. And you create this domain wall in the phases of the plane waves, and now these domain walls they propagate, and then they mix up the interference pattern in here, and this is why you can get all these things. Right, if you think DC, for instance, in DC you are used to 0 voltage, 0 current. But if you think about the way we derived under Whittaker formula and all this theory, it's the get 0 current because the current that comes from one lead is exactly compensated by the current that comes from the other one. Now, if you play around with the interference pattern of things coming from one lead, you can make destructive interference. And this is why, for instance, you could pump electron because one is stopped, but the other one is not. And then you are just getting current coming from the other lead. This is the kind of ideas we are playing with.
Right. Thank you for your answer.
No more? Shall I continue?
Sure. Yes, I think we can go on.
No, we have one question from Takashi. Please go ahead.
I have a question. So I'm not so familiar with the experiment how experimenters can do these experiments. So is it already possible to change the voltage within the picosecond time domains in these devices now?
Almost. Actually, there are very good group in Japan. So you should you should like it.
I know.
It's if you think so, the typical velocity of a voltage pulse is in the 10 to the 5 meter per second, which translate into, so if you make a device micronic sizes, typically you have 10 picoseconds for the voltage pulses. Commercially, you can buy AWJ, so the voltage generators that are in the not yet there. They are, I think, probably the most expensive is 20 picosecond or 30. I'm not sure, but you can almost buy that commercially. But now, so what the experimenters are doing is they are making their own to go below on their hint that 1 picosecond will become accessible soon. So right now they are in the crossover region. So things are not clear exactly, but we can definitely see that this is coming. Yeah.
Thank you very much.
Okay, so okay, I can let me explain the formalism now a little bit. Louis, please stop me when I am when I've exhausted my time.
Yeah, sure. No worry.
So essentially, we want to integrate Schrödinger equation in time. So there will be no complicated things, no Floquet operator or things like that. Just plain integration in time. The one thing I want to make sure we do correctly is to treat Pauli principle. And the reason is this is a typical drawing of the kind of device we will be looking at. Now we think more kind of general. So mostly I will be discussing time binding models. For analytics, continuous is good, but for numerics, time binding is even better. With leads, and the lead is really something that repeats all the way to infinity. So I'm going to, I want really to treat the thermodynamic limit so that when something here gets there, it continues forever. It's not going to mess up my simulation later. Okay. So I have to deal with Pauli principle. I have to deal with thermodynamic limit, and then I will tell you also that there are a few other things, at least one, that you have to deal with. Fortunately, all these things now have been dealt for you in the packages. So essentially, I mean, because it took a while to figure out how to do that properly and nicely and in a way which is effective when you do simulations. But now essentially we know how to do that. So the Pauli principle problem is very simple. Is that, so let's say suppose that you have an electron that flies above the Fermi sea. So this is space and this is energy. And now you have some sort of time-dependent thing. So let's say you shine some light, like a graphene, circular polarized light, something like that. Or it could be changing my voltage gate, it could be anything. So my Hamiltonian-dependent time, which means that this energy is not conserved anymore. So this electron has a certain amplitude of probability to go here, there, and there. But wait, it cannot go there because this is already occupied. And if I don't treat the Pauli principle properly, then my results are going to be really, really very wrong. Ideally, I would also like to take care of electron-electron interaction. This is a subject I will not be able to touch in these 2 lectures. But at the very least, we want to deal with Pauli principle. And so let me tell you the solution for a finite system. You see, the solution is very simple. So I have a very general quadratic Hamiltonian. And now S is only a finite system. I will go to thermodynamic limit a couple of slides later. And I suppose that at time equals 0, I mean time smaller than 0, the Hamiltonian is not time dependent. I switch on the time dependency at time equals 0. So if it is not time dependent, I can just diagonalize this matrix here. This H is just this matrix element. And this C dagger I, Cj are just Pauli, the electron creation and destruction operators. I hope everybody is familiar with that, because I didn't write the introduction. So these are the usual operators. So, but anyway, this H here is just a matrix. This is here we are back to basic Schrödinger equation, discretized on the lattice. So the first thing I do is I diagonalize what I have at t equals 0 before I switch on the time dependent. I have this phi alpha on energy E alpha. Fine. And now I can create this operator D alpha, which is just a superposition of the Ci with this amplitude corresponding to the to my eigenstate at t equals 0. And essentially, this state here is a Slater determinant. I fill all this state up to the Fermi level. And this state is a Slater determinant. And that's my solution at t equals 0. So far, so good. It's much simpler to write it with operator like that than with writing the Slater determinant, but it's exactly the same thing. And you can just check that these operators, they also verify the correct anti-commutation rule, because this one do, and this is just a unitary matrix. Okay, now I switch on. I mean, I want to go to time larger than 0. So I should multiply psi, my initial Slater determinant, by the unitary matrix, the evolution operator. And the evolution operator is just, I should have written the, so it satisfies this differential equation. Now we see I put at here, these guys have operators like the C dagger I, Ci. And you can write a formal solution of that. I didn't, but it's a time ordered exponential of integral of h. That's what you would find in any textbook. Now, what you can do is that you can insert, so this operator is unitary, so you can insert, here I have a product of these. I can insert u dagger u everywhere in between all the d's. And if I do that, I go to the Heisenberg representation, and I find that my state psi of t is just a product of d dagger of t, where d dagger is obtained from the initial d's at t equals 0 by just multiplying by the evolution operator on both sides. Okay, so far very, very basic thing. And now I want to know a bit more about what is this d dagger. And this is where the magic of non-interacting problems comes, that you can actually expand this operator onto the initial basis of Ci on sides. And if you look at the evolution operator, you can actually easily check, you need to calculate a couple of commutators, that this wave function here satisfies the time-dependent Schrödinger equation with initial value at t equals 0 equal to the eigenstate it starts from. Okay? And now if you work out what are the average value of, let's say, the number of electrons on side I, you just need to take the sum of the square of this wave function for all the occupied states. So this might look like complicated algebra, but what it means in practice is that before we would just be evolving one state, and this is what we saw in the previous lecture, mostly like you took at one energy, and also it was mostly one electron picture. Now what I'm telling you is that without interaction, you just need to evolve all the states up to the Fermi level. And automatically, this evolution satisfies orthogonality conservation. So automatically, it satisfies Pauli principle. You're going to get a Slater determinant without having anything to do. So the price to pay is that you have to now, instead of doing the evolution, if you want to look at how wave packet propagate inside the system, well, you have to look at how wave packet evolve in the system. Now, if you want to look at what happened to the Fermi C when I send voltage pulse, you need to evolve all of them. So typically, we evolve 1, 2, 300 different states in time. But okay, it's not a big deal. We can do it. If you have a cluster, you put one wave function on each cluster, and it's easily done. So that's essentially the first answer to the Pauli principle problem. You just solve your initial problem at t equals 0 when it's stationary. You get a bunch of eigenstates, and then you evolve each of them in time as if they didn't know anything about the other, and that automatically satisfies the things. And then to get the number of electrons, you get the number of electrons for each of these guys, and you sum all this contribution incoherently up to for all the occupied states. And I probably, not far away from my limiting time. We'll try to conclude this part now. So essentially, we have already know what. So essentially, that's it. We are solving one. Yes, let me keep that for tomorrow. So tomorrow I'm going to explain you how to solve the problem that to go to terminality limit. So okay, now I want the system to be infinite. And actually, you will see that it will be more of a help than a problem. So this is something I will show you tomorrow. And then I will show you a bit more about how to do calculation in practice. And then I will leave the floor to Thomas Kloss. Thomas Kloss is actually the main developer of T-Quant, so he's much better suited than me to actually show you how to do calculation in practice for a real device. So I stop here, and now I get all the questions that might be there in the audience. And thank you.
Thank you very much, Xavier. Thank you very much for this very nice talk. I see that we have several. Let's start with a question by Yanis. Can you unmute yourself and possibly raise the question? Yanis was asking about, at some point during the second part, you mentioned Majorana fermions, and his question is in the chat and says, why not Dirac fermions? What would change in that case? That's his question.
Dirac fermions. I didn't think about it, but essentially anything that you can, you see a bound state. One way to look at a bound state is let's take a bound state and connect it slightly to a lead, to a reservoir. And then this bound state you will see that this bound state become a resonance. So one way to look at a bound state is like an infinite set of going back and forth between two barriers, or it could be a more complex BR, the 2D BR. So any bound state, whether it's Dirac or Majorana or anything, if you connect it to a lead, you can make it leak, and then it becomes an interferent, an interferometers. On this interferometer, now you can use this lead to actually start to play with it and send voltage pulse on maybe a series of voltage pulse to do some sort of Floquet stabilization of it. So there is a lot of room to play with other effects of these categories. I didn't work out the Dirac case or the Veil case, but I'm sure you can play around with that and find nice effects.
Great. Very good. More questions. There's Prasun Kumar.
No, Prasun is my student, so you can ask a question later.
He has special rights. I also have a question. I was since there are no other questions, I will take the time. I found very interesting the way you are seeing how the Pauli principle is enforced. It's a very interesting way of seeing it. May I think as well that essentially what you have is that if you solve for the full problem, then you have scattering states that are orthogonal.
Yes.
Okay. Can you think directly of more in the time independent case?
Actually. It took me a while to figure out all the connections, but so we wrote a big paper with all the things. It's a bit tedious to read, but everything is there. And essentially, when we started all this business, we were working in Keldysh with lesser grain functions on these kind of things. And then we started to work with like scattering matrices with 2 times. Mm-hmm. And we slowly evolved to arrive at this. At the end of the day, you always have something, it can be 2 times 2 energies, 1 time 1 energy. And here, the choice that we are making now is 1 energy on 1 time, but this energy is the energy in the lead before you switch on something, which is different from the energy you would get if you do a Wigner transform with grain function, for instance. But what I could say is that first, all these formalisms are exactly equivalent. There is a 1-to-1 mapping. I will show you a formula how to get the lesser range function from these things later. And so it's mathematically equivalent. We did the calculation in all frameworks, and they give the same numbers for each time we try. But some things are better than others depending on what you want to do. And for numerics, clearly this wave function approach that actually uses scattering states. It actually uses, when I go to the thermodynamic limit, I will not be using just the eigenstate, I will be using the scattering states. So internally, we use the scattering matrix. Those are far more efficient than grain functions. Algorithms are linear in time and volume, so you cannot get any better. And if you do things naively with grain function, you get the square of that, and that's a terrible hurdle.
Sure. Yes, indeed. No, it's very nice, very illuminating observation. I think it's very nice also for all the people in the school. So I see that we are reaching the end of this first day. Let's see if there's any other question. We had already many questions during the talk. So I would like to thank you again, Xavier, for your talk. Thanks again to all the speakers. Thanks, Takashi, Mark. Takashi is well past midnight. so thank you very much. And let's meet again tomorrow. Tomorrow we start again at the same time. And we'll have the same 3 speakers, and so we'll have the second session. So see you all tomorrow, and thank you again.
Thank you.
Thanks. See you.